Alright, so this video is going to be on surface area with parametric equations. Alright, so previously with our regular surface area, right, we're dealing with a regular equation. When we rotated a curve about the x-axis, this was our formula, okay? Well, when rotating about the x-axis with a parametric equation, this equation really doesn't change too much, okay? We're just plugging in our parametric arc length equation. So you can see here, we'll end up with the surface area equaling the integral from alpha to beta of 2 pi y, and then we plug in our arc length equation for parametric equations. So we end up with dx dt squared plus dy dt squared times dt. All right, and that's really it. And for rotation about the y-axis, you get the surface area. I changed the bounds this time, so now we'll go from, let's say, w to z, all right, just to whatever. All right, 2 pi x, and then you have your parametric arc length equation there. Okay, so really not too much is changing here. All right, it's not, it's if you remember your parametric arc length equation, you'll be fine with this. All right, so let's do a quick example. So we have our problem up on the board here. Find the surface area of a solid obtained by rotating x equals r cosine theta, y equals r sine theta from 0 to pi about the x-axis. Okay, our surface area equation for when we rotate about the x-axis is the integral from alpha to beta of 2 pi y times the square root of dx dt squared plus dy dt squared dt. Okay, so now just find dx dt, find dy dt, and you already know your bounds, and you can just plug in and figure it out. So dx dt is going to be equal to this derivative, which is just negative r sine theta, and dy dt is going to be the derivative here, which is just r cosine theta. All right, so now we can just plug in here, right? We have that the surface area equals the integral from 0 to pi of 2 pi times y, which is r sine theta, times the square root of, this will be negative r sine theta squared. All right, that'll be the whole thing squared, so that's going to be r squared sine squared theta. That's going to be added to this piece squared, which is r squared cosine squared theta, d theta. All right, now, what is this whole thing going to be? Well, that's just going to be r. Why is it going to be r? Factor out an r squared here, so you get an r on the outside, and sine squared plus cosine squared is just going to be 1, okay? So really what we get here, we can pull out this 2 pi. The surface area is equal to the integral from 0 to pi of, well, 2 pi, the integral from 0 to pi of, this will be r squared sine theta d theta. All right, and of course this r is a constant too. This r squared is a constant too, so we can actually pull that out as well. So we can just say 2 pi r squared, the integral from 0 to pi. All right, same thing, just might help you a little bit. Okay, we integrate sine of theta. That's just going to be negative cosine theta. So we get surface area is equal to, we can flip these bounds, I guess. I mean, whatever is comfortable for you, just to help deal with that negative that you get. Get 2 pi r squared times cosine theta evaluated from pi to 0. All right. Well, first we need to plug in 0 to theta, okay? And that's going to be 2 pi r squared times cosine of 0, which is 1. We're going to get minus 2 pi r squared cosine of pi. And cosine of pi is negative 1. So altogether, this gives us 4 pi r squared. And that sounds pretty familiar, right? Well, what are these parametric equations representing? Well, it's representing a circle, right? Yeah. But when we rotate it about the x-axis, what do we get? Well, that's a sphere, okay? And this is the surface area for a sphere. So we just found the surface area for a sphere by using parametric equations. So another great example of something that you already knew 10 years ago, but now we're figuring out with calculus. Alright, so that's going to do it for this video. So if this video helped you, make sure to leave a like and subscribe by clicking my icon in the top left. You can also view the playlist for parametric and polar in the next video in the series. See you soon.